All right, so this is section 4.8 of Math 146. We're going to be talking about the double angle, the power reducing, and the half angle formulas. The irony is all of these stem from the sum and difference formulas that we did in 4.7, which is kind of why I like to do that first. It just makes sense because in this case, I'm actually going to show where all of these angles come from. Excuse me, where all of these formulas come from, and the fact that they do stem from the other one. So I won't spend an extraordinary amount of time doing it, but I am going to show it, and then we'll do a few examples because pretty much the idea behind these formulas is they are just more formulas that are going to help you in solving specific problems where maybe everything is not currently in terms of unit circle values, but maybe we can get them there. All right, so let's start off by first I'm going to state what the double angle formula is for sine. So the double angle formula for sine is sine and double angle, meaning it's 2 times theta. That's now the angle. We have a double angle in there. And that formula is 2 times sine of theta times cosine of theta. Okay, so that's the actual formula. And if nothing else, you could always just memorize that formula and you'd be good to be able to use it. But where does this actually come from? Well, if you think about it, 2 theta is really theta plus theta, correct? I mean, it's the same thing. So you could really rewrite this, I'm going to do this over here, as sine of theta plus theta. Well, using our sum and difference formulas from 4.7, that is the same thing as sine of theta, because that would be sine of the first angle, cosine of theta, well, that's the second angle, plus cosine of the first angle, plus, times sine of the second angle. And of course, what you have on the right-hand side, this sine of theta cosine theta, plus, technically, if you were to rewrite it, sine of theta cosine theta, so you have 2 of those. 2 sine of theta cosine theta. And again, sine of theta plus theta is the same as sine of 2 theta. So that's where that comes from. For cosine, there's actually 3 different forms you can use. Really, all you need to know is the first one because you can establish the other 2. But cosine of a double angle is going to be cosine squared of theta minus, sine squared of theta. And I know that looks very similar to cosine squared plus sine squared, which would be 1, and it's not the same thing. So just make sure you don't get that confused. And again, that is established from the fact that we could write cosine of 2 theta as cosine of theta plus theta. So in this case, your first and your second angle are exactly the same. Well, using your cosine formula, that would be cosine of the first angle times cosine of the second angle, and again, they happen to be the same. Because it's plus, we change the sign to minus, and then it is sine of the first angle, sine of the second angle. So ultimately, you get cosine squared of theta minus sine squared of theta. And that's where that's established from. The other 2 formulas for cosine, again, you don't necessarily have to memorize these, but they will be useful for the future, is that cosine of 2 theta is also equivalent to 1 minus 2 sine squared of theta, or cosine of 2 theta is equivalent to 2 cosine squared of theta minus 1. Now, where do we get those from? Well, the general idea is that you're going to take your standard cosine squared of theta plus sine squared of theta equals 1 identity and rearrange it. So if I wanted to solve that one for cosine squared, I would subtract 1 on both sides. I'm sorry, I would subtract sine squared on both sides. And then what you could do is you could take 1 minus sine squared and you could substitute it in here for cosine squared. And then you would have 1 minus sine squared minus sine squared. Well, if you combine those, that gives you this one. And then likewise, instead of solving this equation on the right here for cosine squared, I could solve it for sine squared, and then I could substitute it into the sine squared here, and that would ultimately give you the second one. I'm not going to walk through the algebraic process there, but I'm pretty sure you could figure out pretty quickly that's how you would get it. So these are really the two that we need to know. And as long as you know your sum and difference formulas, and you don't want to necessarily memorize these, although I strongly suggest going ahead and doing so anyway, you could always establish them by doing a sine or a cosine of theta plus theta, and that's how you establish them. All right, so now how would I actually use this? These are the double angles, by the way, so we're talking about this particular one right here. So we could use it if a problem said something like, well, let's see. We're going to be told that sine of theta is 3/5. We're going to also be told that theta is going to lie in between pi halves and pi. And again, the importance of that is now we know that that is in the second quadrant. That will help for our positive and negative signs. So down here, if that's the information you're given, you might just want to write that that's quadrant 2. And we might be asked to find the sine of 2 theta, sine of twice the angle. Now remember, you're not just doubling 3/5 because that's what the sine of theta equals. It's not the angle itself. So in order to do this, you're going to use the sine of 2 theta's formula, which is 2 sine of theta cosine of theta. Well, they gave us what sine of theta was in the problem, so we can literally substitute 3/5 into that. The problem is that they didn't give us the cosine theta part, but because of the fact that we know that from the right triangle, and if that's my theta, then sine is opposite over hypotenuse. Using the Pythagorean theorem, we find that the adjacent side would be 4. Okay, that's a 3, 4, 5 special right triangle. And now we can figure out that the cosine of theta, because of that, is going to be 4/5 adjacent over hypotenuse. And the fact that it's in the second quadrant lets us know that that is a negative 4/5. So now I can substitute a negative 4/5 in for cosine of theta, and just going ahead and multiplying everything out here, we are going to get, let's see, 2 times 3 times 6, I'm sorry, 2 times 3 times 4 on the top is going to be 6 times 4 is 24 over, and then 25 in the denominator, and it will be negative because I have a negative 4/5 that I'm multiplying in. So the sine of 2 theta, based upon the information given, was negative 24/5. And that's the general idea of how you could use this, at least in one specific case, how you could use that identity. All right, and because it is not as heavily used, I am going to give you the tangent of the double angle. Again, it would be established by doing the tangent of theta plus theta. I'm not going to walk through that process, but ultimately it simplifies down to 2 tangent of theta over 1 minus tangent squared of theta. Should you need to use that for any reason, that would be a formula that at this point I would just know for the purposes of using. Again, it's not as heavily used. I am not going to stress it. I'm not even going to do an example here of that one. But again, if you need to use it, then there it is for you. Let's move on to, let's do the second thing, which is the power reducing. This one I can tell you is probably one of the more essential trig identities that you'll use when it gets to higher level calculus work, whether it's in Calc 2 or Calc 3. The power reducing formula comes up quite frequently. And what it says is that if I have the sine squared of theta, that is equivalent to 1/2 of 1 minus cosine of 2 theta. The nice thing is, if I have cosine squared of theta, it is almost exactly the same thing, but it is 1/2 of 1 plus cosine of 2 theta. Oops, forgot an extra parentheses there. Okay, so where do those things come from? Well, both of these formulas come from the cosine of a double angle formula. So if I were to simply start off with the fact that cosine of a double angle, now we're going to use one of the other forms of this. We're going to use 1 minus 2 sine squared of theta. Well, if I want to solve that for sine squared of theta, I would simply subtract, or actually, let's do it this way. Let's add the 2 sine squared of theta to both sides. I'll do this in multiple steps. So we'll add that to both sides. And then we're going to subtract the cosine of 2 theta on both sides. And then you would divide both sides by 2. Dividing by 2 is the same thing as multiplying by 1/2. So I would multiply both sides by 1/2, in which case I have now established the sine squared reducing formula. If you want to establish the cosine squared one, you would use the other cosine squared other cosine of 2 theta, which is the 2 cosine squared theta minus 1. Manipulate that to solve for cosine squared, and you would get this one. So the one I just solved was that one right there, and that shows you that that's where it comes from. So again, it all stems from one formula, which just needs to be manipulated. And what's the advantages? Well, there's going to be certain times that operations are going to be easier to do if things are not in a squared form, but they're in a non-squared form. I'm not going to jump way too ahead, but when you get to calculus, you will understand that this is the case. There's also a tangent squared one. Once again, it's not something I am going to prove. However, the easiest thing to do here for tangent is to realize that tangent is, of course, sine over cosine. So tangent squared is sine squared over cosine squared. Well, if I were to literally put what I have here for sine squared over cosine squared, the 1/2s are going to go away, and you're going to be left with 1 minus cosine of 2 theta divided by 1 plus cosine of 2 theta. Once again, not something I'm going to go into heavily, but that definitely is something that if you need to use it, there it is for you. And that one's one of the easier ones to figure out as far as how to establish it. All right, so again, those are the sine and cosine squared reducing formulas. You reduce these formulas to something which no longer has a square in it. All right, let's do an example. Oh, come on, extend, there we go. Let's do an example where we want to solve the equation sine of theta cosine of theta equals -1/2. And we're going to say that in this case, theta is going to lie in between 0 and 2 pi. So we're just basically going to find the values of theta on one unit circle that are going to make this true. Well, hopefully you can recognize that that is very, very close to being the identity of 2 sine theta cosine theta. We're just lacking the 2. But I can introduce the 2 if we want to, simply by multiplying both sides by 2. Excuse me. So then I would have 2 sine of theta cosine of theta. And the reason I do that is because now it's going to create a double angle. Multiplying the right side by 2, you just get -1. So now what I can do is I can rewrite the 2 sine theta cosine theta as the sine of 2 theta. And again, the reason for doing that is because now I can say, well, where is sine? Don't worry about the angle part yet. Where is sine going to equal -1? Well, on one normal unit circle, sine would equal -1 at 3 pi halves. However, the fact that this is a double angle means that I actually need to go one more full circle of values, which would mean if I add 2 pi to 3 pi halves, that is going to get me to 7 pi halves. And you might say, wait a minute, that's outside of 2 pi. And you would be correct. But remember that the angle presented is a double angle of 2 theta. If I want to solve that for theta, I need to divide both sides by 2, which is then going to give us the answers of 3 pi fourths and 7 pi fourths, both of which are actually within 1 unit circle. So those would be the solutions to that specific problem. All right, and the last thing we're going to talk about are the half angle identities. And again, both of these are going to come from the fact that we already know some of the other identities. So let's actually just go ahead and establish the half angle identity for sine first. So what we're going to start off with is, let's just say that we have sine squared of theta. And we know that by the power reducing formula, that's going to be 1/2 of 1 minus cosine of double the angle. Well, if I want half of the angle, so if I'm going to replace theta with half of its angle, now what I'm going to have is sine squared of theta divided by 2. Oops, there we go. Theta divided by 2. Well, then that means I'm going to replace theta on the right side with theta over 2. But the nice thing is, when you replace theta with theta over 2, now I've got 2 times theta over 2. Well, that's just theta. So now what I have is sine squared of theta over 2 equals that equation on the right, expression on the right-hand side. If I want to solve for sine of that specific angle, sine of a half angle, well, that means I have to take the square root of both sides. I'm going to slightly rewrite what's on the right-hand side as 1 minus cosine theta over 2. So just distributing the 1/2 to the entire thing. But I took the square root, which means that I need to also take the square root of this side. But don't forget, I took the square root of both sides of an equation, so I have to include the positive and the negative. And that square root symbol, I should make that a little bit better, is over the entire fraction. So our first formula is that the sine of a half angle is the plus or minus square root of 1 minus cosine theta divided by 2, all under the square root. Okay, cosine squared can be established the same way. I'm sorry, cosine of half the angle can be established using the same basic principle, which I'm not going to walk through, but you would basically do the cosine squared stuff on the right-hand side. So hopefully you would realize that that's going to pretty much be the exact same thing. But remember, cosine inside the parentheses on the right-hand side over there was 1 plus, so it will be 1 plus cosine of the angle over 2. And then once again, not going to go through the entire tangent one, but as you can imagine, tangent would be the same basic idea, since we already established what tangent squared was above just by dividing sine and cosine. You will see that tangent ultimately is the same general idea. So tangent of the half angle will be plus or minus the square root of, and this time it will be 1 minus cosine theta from the sine part over 1 plus cosine theta from the cosine part. Notice that there's no over 2's because those both canceled out with the tangent part. And again, the plus and minus sign is there because you're taking the square root on both sides. So how would we use this? Let's do a quick example. So let's say that we want to find the cosine of 15 degrees. So we know in this case that 15 degrees is the same thing as 30 over 2. So 15 degrees is the same thing as 30 degrees divided by 2. Well, that's what's going to help us. So now we're going to use our cosine of a half angle formula. cosine of theta over 2 is going to equal plus or minus the square root of 1 plus cosine of theta over 2. And the biggest thing is we have to realize here, because we're trying to find the cosine of 15 degrees, we're really letting theta equal 30 degrees so that we can get to that 15 degrees. So we're going to plug in 30 degrees as our theta, and that'll give us 1 plus cosine of 30 degrees here over 2. This is not going to be a very pretty answer, just letting you know that. So that will give us the cosine of 15 is equivalent to, just a little bit bigger, cosine of 30 degrees is square root of 3 over 2, so we get the square root of 3 over 2 all over 2. Dividing each fraction on the inside of this root by 2, you get 1/2 plus the square root of 3 over 4. And if I want to combine those fractions, which I can, I probably shouldn't have uncombined them in the first place, if that's even a word. We'll make that 2 plus the square root of 3 all over 4. And the only reason for doing that is because now I can separate my square root on the top and the bottom. I can't really do much with the top. It's going to be pretty ugly. It's going to be the square root of 2 plus the square root of 3. And then the denominator, no longer under a square root, because the square root of 4, of course, is 2. Not a very pretty answer there, but that is how you would figure that one out. And then if we wanted to find the exact value based upon some non-unit circle type stuff, and this one will probably be our last example. So let's say that we are given that cosine of alpha is -3/5. We are going to be told that alpha lies in between pi and 3 pi halves. So now you know the quadrant it's in. And maybe we want to find the exact value of sine of alpha over 2. So we are trying to find sine of alpha over 2. That's our goal. Well, again, the fact that we've got alpha lying in between pi and 3 pi halves tells me that that is quadrant 3, so that helps. I'm going to go ahead and write the formula that we know for sine of alpha over 2, which is going to be plus or minus the square root of, and since it was sine, it's going to be 1 minus cosine of our angle divided by 2. Oops, should not use theta there since we're using alpha. So what do we have to let alpha be in this case? Ultimately doesn't really matter that much because we're going to use this, but we're going to figure out that we already have the cosine of alpha. They gave that to us. Perfect. So the sine of alpha over 2, put those in parentheses, is going to be plus or minus the square root of 1 minus the -3/5, so plus 3/5 over 2. Okay, let's simplify what we have there. That's going to be, let's see, in the numerator, that's going to be 5/5 plus 3/5, so that's 8/5. So we'll have 8/5 divided by 2. Dividing by 2 is multiplying by 1/2. So we get plus or minus the square root of 8/5 times 1/2, which is going to give you 4/5. Separating the root on the top and the bottom, we're going to get the plus or minus 2 over root 5. And then if you rationalize, that would be multiplying by square root of 5 on the top and the bottom, plus or minus 2 root 5 over 5. And again, this is great, but we're not quite done because that represents the half angle. So plus or minus 2 root 5 over 5 represents the half angle. So in order to actually solve for alpha in this case, you would need to multiply everything by 2. And multiplying every piece here by 2 is going to get you plus or minus 4 root 5 over 5. So we've done two things in that particular problem. We solved for the sine of alpha over 2. That was right here. And we actually solved for alpha if we needed to know what that was right here. The biggest thing was, and I didn't actually fully solve this problem, we're going to finish it off here in just one second. I did solve for alpha over 2, but remember I have a plus or minus there, but we established that this is in quadrant 3, which actually means that we have to do just a little bit of work to figure out where alpha over 2 is actually going to be, because that's what we're interested in here. So if we go back to the fact that they told us that alpha lies in between pi and 3 pi halves, but we're really looking for alpha over 2, which means that if to get alpha over 2 out of this, you would have to multiply everything through by a half. So alpha over 2 is actually going to lie in between 3 pi halves and 3 pi fourths, which actually puts us into quadrant 2, which means from all of this that this is actually going to be the positive of 2 root 5 over 5, because it is going to end up being in quadrant 2. So our final answer for this is 2 root 5 over 5. That is the sine of alpha over 2. All right, I do believe that that is plenty enough for this particular lesson. That actually finishes off Unit 4 completely. We will come back with Unit 5, and we are going to get into some applications involving right triangles, including the law of sines and cosines. And Unit 5 is only 3 sections long. As a matter of fact, the remaining units are all 3 sections long. So we will come back with Unit 5.